So let's drop down a sphere that will act as a source for smoke. Next, we go to the pyro shelf. As we use billowy smoke, we can find that it has created a simple smoke simulation for us. Let's play the animation. Also, we can find in the network editor that all the necessary nodes have been created with the default settings. As we dive inside top network, we find the network which is very similar to what we used to have in the previous versions of Houdini. I am showing this tutorial in Houdini 17.5. Now this import node is simply showing density imported from top network. But when we dive inside the object node network, by default the network here is different from what we used to have in the versions before Houdini 17. In the previous versions we used to create source volume directly from the object, be it density or velocity volume, whatever. Now here Houdini has scattered particles or points on the surface of objects, and these points are then associated with attributes like density and temperature. These values are randomized and they are animated over time. As you can see from the spreadsheet, we play the timeline and these values are changing. Now here we click this icon and we can visualize the attributes as varying colors. Okay, finally, after the necessary attributes are in place, eventually they are converted into volumes. Well, in the previous versions, Houdini 16 and before that, when we created source volume from a surface or a curve, or say we wanted to create velocity volume from animated particles, a lot of times we had to struggle finding the right way to create the volumes from it. But now it's the standard way. It's simple and they claim it's fast. First create points or particles, create density or use its velocity to create volume, then fetch the volumes using volume source inside top network. Okay, let's say instead of sourcing from the surface of object itself, we wish to source smoke from particles. So let's birth particles. And we'll use the first context geometry. Let's have 500 such particles per second, and let's add some upward force. So give it a value of say 1. A little bit of amplitude there as well, and as we can see the particles are moving up with slight variations. Also we would like to add this node called pop axis force. Okay, now let's increase its sphere of influence, make it sufficiently large, and now as we increase the orbit force, we will find, let's play the animation, and we will find that the particles are revolving around an axis, in this case around y-axis. Now let's dive up and we wish to use these particles as source. So let's plug the out into this network. In this case, instead of using source smoke, instead of surface scatter, we will use keep input. So let's dive inside top network and allow simulation to play. Yeah, the particles are emanating smoke. Now, now for a better display, we can add light by rotating our camera to the direction we wish the light to come from, and control click. This will add the light. Now as you can see that it has given us a better 3D display. The light is coming from a side and we have shadow on the other side, so instead of a flat looking smoke, now we have an interesting smoke display. And this is so smoke is sourced from the particles as intended, achieved without much of a hassle. Now in this case we wish to source smoke from an object, say torus, but velocity is to be derived from particle animation happening in a different chain. Now this is a simple particle simulation with an upward force applied and a small orbit force as well, so the particles are revolving around y-axis. Let's move one level up and create the necessary structure for density volume. So scatter points on the surface, so as usual we will use the pyrosource. And in this case we will use surface scatter and not keep input. Now as you change the initialize method to source smoke, this will add density and temperature attributes which we wish to vary over time. Adding density and temperature attributes, we will add animated. As you click this icon, we can see that the colors are animating across, showing that the attributes are changing over time. Also, last but not the least, we will add volume rasterize attribute to finally create the volumes from these attributes, the density and temperature attributes. Now as we play with these values here, we can see we can achieve even harsher, we can achieve good contrast. So density appears for some points and almost nothing in other points. Let's play it and you can see that yes, the density is varying. So add null at the end of the chain here and we name it density, so when we fetch it through the source volume it will be easier to locate. Now if we look at this side, we can find all sort of attributes coming out from pop network. If you click here, you can see that all the attributes are there. So let's delete them first. We will add attribute delete and let's remove all these attributes. The point attributes, we want to delete them. Primitive attributes also gone with this, detail attributes and the vertex attributes also, let's delete them all. But in the process we have lost the velocity attributes that was available to us, so we should have kept it, but then it's okay, fine. We can create velocity using trail, and from these options we can choose compute velocity. So in the geometry spreadsheet we have velocity available again. Now when we had used pyrosource node earlier, it has created the p-scale attribute here. It's very essential, so we need to add one on this side as well. So let's take attribute triangle. Here instead of giving it a value of 0.1 or 0.2, say anything, we would like to create a slider here, chf my p scale, and as I press the button here, it will create a slider. Now we can change the value here. Now let's create the volume for velocity, and the velocity attribute here will be v. Let's end this side of the chain with a null. Let's rename it as out velocity. Now that our volumes, density and velocity both are ready, let's create the DOP network. Let's dive inside. Let's create the most essential pyro solver, and we will like to create smoke object also. This will act as a body or container where simulation happens. We are keeping the number of voxel count low at the moment, which means the size for each voxel will be large, means a low resolution for simulation. But for the sake of this tutorial, so that the simulation happens faster, let it be. One thing, we obviously have to increase the box size of smoke object. So let's resize it, and now fetch our volumes using volume source. So torus object out density. Now density is scalar. Source volume will be density, and target field will be density. Okay, let's duplicate this, and this time velocity is coming as v. Let's fetch it the path. It's going to be outwell. Let's merge these two together, and then we will plug it into the last input. Okay, plug in there. Now there is a cool way of optimizing the calculations. We will dynamically resize the smoke object, so only the voxels where density appears come into play, and later as needed, as the smoke reaches outwards, the voxels then will be calculated. And the way to do this is through gas resize fluid dynamic node. Okay, let's dive up and let's visualize data density. Now as we play the animation, I think we might have to scale up the velocity value as well. Give it a value of 5, then play the animation, and yeah, as intended, we have density sourced from surface of torus and velocity is derived from particles. However, one thing you might have noticed, for some of the voxels density is there, density has appeared, but the particles animating might still be reaching there, not reached there, or simply the particles might not have been birthed yet. So means density has appeared but no velocity to guide it. Might actually be much more happening inside Houdini, but we can assume this way. Let's say these squares are voxels, and as density appears here in this voxel, we want the velocity value to be present there already, derived from the moving particles, thus giving direction to density and smoke to flow in that direction. So in a way, we wish to have velocity values or velocity field present there even before the density appears. So let us see how we can achieve this. So let's prepare the velocity field, and this we will create from the velocity derived from particles itself. So we will freeze the movement of particles first. Let's take time shift node. Okay, let's scrub the timeline to find a proper frame. I think frame number 75 is the right candidate. So we know that we have the velocity values available to us. Now it's time to create an area to scatter points. Drop a box, resize it, create a scatter node, and let's scatter some points in it. Since we want the points scattered all across the volume of the box, inside the box, and not just on its surface, let's first create fog. Let's scatter 5000 such points. Now these points will share the velocity values from particles, and for this we will take an attribute warp. This is going into first input, this is second input, and let's dive into the warp, attribute warp. Let's drop a point cloud, open node, connect point position to positions, and output 2 to file input. Now the way this point cloud system works is we'll query the velocity value for a few particles around every point, average its value, and copy that velocity value to the point using bind export node. Okay, let's jump out, and we see that we have the velocity values associated with points now. No velocity. Okay, there we have. Now just in case we want to visualize the velocity values, we can generate such a visualization with a volume trail. Now since this is going for visualization only, let's lower the point count, say to 500, and the other input requires a velocity volume. Okay, we will have to create a velocity volume, so add a volume, plug in the bounding area for volume. Okay, now this velocity volume has no values at present, and we need to supply this with velocity values from particles. So let's drop volume warp. This is very much similar to the attribute warp, but it works with volumes. In fact, we can dive inside the attribute warp and we can copy these nodes. Let's go back to the volume warp and paste it there. Very handy. Okay, so connect these two, connect the output 2 with the file as well. So we are now querying the values for velocity, and let's dive back up, and now we make the necessary connections here, just like the way we had set up in the attribute warp. Okay, connect this one, and this is not showing. How come? Oh, the reason is simple. We have to increase the number of points, so every point can find some particles around to query velocity values. And let's increase the search radius as well. Yeah, we are querying V. Okay, we wish to output velocity actually. Well value we will want to. There we go. We now have a very good way of visualizing how the velocity flows across the field. Okay, I think we might need to increase the size of box here. We can increase the search radius as well. And then the same settings we need to apply for attribute warp PC open node as well. Increase search radius and the number of points. Okay, let's increase the number of scattered points again back to 5000. You remember we reduced it earlier since we wanted it for visualization purpose only. Also the size of torus here, I think it's very small. Let's increase it somewhat. Also, one thing I would like to add, inside this attribute warp here, let's add some noise into the velocity. So let's add curl noise, and we will add this with velocity. Let's play with the frequency settings here. 0.8, okay, that will do. The rest let's keep it as it is for the moment. Okay, we need to connect this with the binds export node. Okay, now let's jump up a level and let's check our simulation. Let's play it. Oh, fine, this is working. So we have density coming from torus, and we have the velocity coming from particles, particle field that we have created. And yeah, just remember that we have kept the resolution very low everywhere, but that was just for the sake of this tutorial. We wanted the simulation to happen faster. Okay, carrying the same concept forward, now we would like to give direction to the smoke using a curve. So now let's dive inside this curve object, and this is the setup that I have already created. And what exactly we have done here is, this is the curve. This is responsible for giving the direction. We are creating basically normals here, and the normals are going to be the velocity source for the velocity volume, whereas this sphere here, this is going to be source of our density. So let's check what exactly we have done here. This is the curve, and all we have done here is given it normals. If you want to visualize the normals, all you have to do is just select it and press X, and this is the vector value. The attribute we have provided is we want to visualize is normals, and as you can see, the normals are going downwards, but what we want is the normals to be reversed. We have given it a simple Vex expression to reverse the normals, And now these normals are going to be let me visualize this thing as well. So these normals are then going to be uh, the source of velocity volume. So first we have the region where the volume exists, and then we have created the necessary volume. This is going to be fog volume, and let's scatter some points inside it. The normals from here, I need to somehow provide that information to these scatter points, and the way we do so is again through PC open node. This is similar to what we have done earlier as well. The normals are coming from output 2. Yeah, the normals are coming from here, and we are querying normals, but then we are adding a little bit of curl to it. This is a vector attribute. All we are doing is now outputting it as a velocity attribute. So once we have points with velocity values, all we have done is appended a pyro source node to it. So this has created velocities. We might have appended p scale values to it as well, and then simply created a volume from it. Now this side of the chain is again a simple setup. We have the sphere here. We have created the necessary density and temperature attributes, added a little bit of noise, and finally converted it into volumes. Let's dive up, and as you can see, the curves normals are now giving direction to the smoke. Okay, thank you.